I'm Matt Norman. I'm from Oak Ridge Leadership Computing Facility, and I'll be talking quickly today about what do you do when you have really small neural networks you're trying to integrate into your Kokkos code. I've looked for a lot of tools for this. If you have a really large neural network, it really doesn't matter. You can offload that using SmartSim or some other tool to a farm of Python nodes. Because you can afford the overhead because it's going to take a long time to inference a model that has millions to billions of parameters. But if you have a model that has tens to hundreds of parameters, the situation is quite different. The example that I want to show is if you have like a finite volume method that's time explicit, doesn't require any global linear solves. Everything in the entire simulation really depends on what you do on these small little stencils of order 5 to 10 cells. So if you wanted to deploy a neural network there, where it's going to be done every grid point, every time step, possibly trillions of times throughout the simulation, then overheads really matter, and how do we reduce those as much as possible? We do have C++ backends for frameworks like PyTorch and TensorFlow, probably quite a few others. But if you read the documentation and try them out, you'll probably find that the performance characteristics are a little bit opaque in the documentation. It's not clear how many kernels are running. Oftentimes they load data through stud vectors, and it's not clear if you have to just move that to the GPU every single time. So this is kind of a proof of concept of how can we conceive of something that can be quicker. I've written a prototype code on GitHub called Portable Online Neural Network Inferencing. Really, I just made that to get the acronym for PONY. So lots of puns to be had there. But this uses C++ templates and tuples to recursively iterate through the tuples that you define, every element of the tuple being a layer, quote unquote. You can do it streaming through the dynamic access memory in batch mode, or you can have everything just kind of sit on the stack locally in the kernel. Obviously, stack will perform the best if you don't overflow registers. So when possible, that would be the best way. But there are caveats that make that harder to code we can discuss later. You can do it all in a single kernel, or you can actually integrate the neural network inside a kernel with other code, which is really convenient when you have like a stencil that you're gathering for the inputs, and you don't want to have to just flood all the different stencils into an array, because that would multiply the amount of memory you need by 5 to 10 times. So I have tried with half T and B half T, the brain float, quote unquote. And there's not a ton of layers. You can do dense nets, res nets, and MLPs, which is multi-layer perceptron, not My Little Pony. And you can use non-backpropagation based online training as well that I played around with too. So what does it actually look like in code? This top block here is defining the layers. We'll have your typical dense layer with a matrix vector multiplication, a bias. We'll have a ReLU activation. With a 0.1 negative slope, so it's a leaky ReLU. And we're loading these weights in that were saved from a Keras file, so there is capability to kind of conveniently bring in something that you saved from Keras or PyTorch. And then in this line down here, there's a convenience function that will construct the tuple and create your model for you. You can print some information about it, and then the inferencing done in a kernel on the device is just done in a single line, and then you can process your outputs from there. There's also the ability to do this inside a kernel. If you do have register pressure in your kernel for whatever reason, you may want to stream through the DRAM using, these are YACL arrays. Really, they're Kokkos views. YACL is now a Kokkos layer instead of yet another kernel launcher. But again, it's just a one-line inferencing done inside the kernel, and then you can take your outputs in the variable out and use them to do whatever sort of magic you want to do inside your algorithm. Because typically we want to use neural networks to convey something in the code that's not well described by PDEs or equations, that just behaves better than what we've constructed ourselves. Take a look at what it looks like to do it in stack mode, and this time with half precision. You just use the Kokkos experimental half T. And in this case, you're going to define these S arrays are just fixed size Kokkos views, essentially. It's just wrapping a normal stack array. and load those into the inferencing after loading in the inputs, and then you can use the outputs without really touching DRAM as long as it fits in register, which I've been surprised by how large. You can get several hundred parameters in these models and not overflow registers from my experience, so that's kind of nice. How to train your pony. If you actually wanted to do online training, you will create a type and object using decal type, I think is the most convenient way to do it. And then you can store this in the class or in static or namespace. And then you're going to overwrite that with a specific model that you want to allocate for your situation. It will tell you how many trainable parameters are inside the model, and you can have an external optimizer set those as a 1D array. And then test the results, create a loss function, go back to the optimizer, and that's how we can do an online training. One of the test cases I've looked at here is you have weighted essentially non-oscillatory limiting. I don't have time to describe that if you're not familiar with it, but you're just combining multiple polynomials to make things less wiggly is the ultimate goal. And so I wanted to simplify this to just take a 9th order and a 1st order reconstruction and combine the two with a weight that's adaptive to the stencil. The neural network then uses that stencil to create what that blending weight is going to be. This particular model had 65 trainable parameters. There were 40 million training samples where I was tensoring out every possible stencil combination you could get for typical advection. And about 100,000 training iterations using Meta's Nevergrad tool. Covariance matrix adaptation evolution strategies is the one that seemed to work the best, and it took about 5 minutes on a single AMD MI250X. And I was able to get, using this approach, just about a 15% error compared to the original Wino behavior with this much simpler approach that runs significantly faster, probably about 10 times faster than the original Wino did. So looking at some of the performance, this is a lot, but these purple arrows that we have here, this is where I did the batch mode and ran things through DRAM using Kokkos views. This will be expected to be slow because you're not doing it in a register. And then the yellow arrows is looking at things that we're doing local stack computations. So all of the local stack computations performed about the same for the kernel, but keep in mind that the neural network is running at the same time as Wino reconstruction and high order and 1st order reconstruction. So they're all sitting there in the same kernel with the neural network. And if you look at this red line here, anything above that red line is the overhead of the neural network itself. So as long as we're running in the stack and register, you can barely even notice about 10% overhead. The half T and B half T runs a little bit faster than half T in terms of the computations, but something weird happens when you run through DRAM. The B half T's for some reason seem to transfer like floats. I don't know if they behind the hood actually take up 32 bits instead of 16, but when you transfer them, they don't transfer twice as fast like you would expect, like half T does. And I don't know the reason for that because I haven't had a chance to really look into it yet. Just looking at pros and cons in future work, you do have control over the performance with this. You can do it as a single kernel or in the same kernel as other work, and you significantly reduce the overheads. And largely, the code that's using the neural networks doesn't need to know about the neural network architecture. That's all kind of done, behind the scenes. The cons is you have to organize the layers yourself when you're creating these tuples, and that is error prone. So it is what it is. And you have to create new layers as needed. There's very few implemented in the prototype so far. And different frameworks will have different ways of dumping out their data. Some will transpose it like PyTorch does compared to Keras, so just keep that in mind as well. These are all bug-prone cons. For future work, I'm looking at doing integer quantization for the neural networks myself rather than using half-precision types because integer ops tend to be quite a bit cheaper. And maybe there's room for using a chatbot to develop new layers or organize the layers for you from a PyTorch file or something like that to make it a little bit less error-prone. But I'm happy to discuss other possibilities, other work that people have done in this particular niche area of neural networks. But thank you.
Thank you, Matt. Rick?